Well, good morning. Today we are going to do Chapter 7 Aqueous Solutions. But before we do that, on Wednesday we are doing the empirical formula lab. And I just want to make sure everybody's up to speed on this because it's a lab that's a little bit, I would say, dangerous. So you have to really be careful with it. All right, let's just review empirical formulas. Basically, it's a mole ratio. It's the lowest whole number ratio of elements in a compound. We've seen glucose many times. Glucose is C6H12O6. What you do is you look at the formula, decide which one is the lowest subscript, and then you divide everything by that. So 6 divided by 6 is 1. 12 divided by 6 is 2. This is a 1. And we get CH2O as our formula. Now, empirical formulas don't tell you much other than the mole ratio. This is glucose. It's obviously very different than acetic acid. And yet they have exactly the same empirical formula. But the empirical formula is what you get when you do analysis. And that's what we're going to do on Wednesday. We've seen magnesium ribbon burn. Very brilliant. Make sure not to look at it when you're doing this. Reacts with oxygen and gives magnesium oxide as a product. The question is, what is the empirical formula for magnesium oxide? What you're going to do is take a little length of magnesium ribbon, wrap it around a pencil or your finger or something so that you can fit it into a crucible. You want lots of airspace around there, but at least on the bottom it has to be touching the crucible itself. You will put this on a ring stand with a clay triangle, and you will start heating the heck out of it. When you do, the magnesium will light on fire. Again, be very, very careful because this is extremely hot. And as the reaction proceeds, it gets even hotter. You're heating this whole assembly up to red heat. So, got to really be careful with this one, guys. To get the empirical formula, what you do is you need the number of moles of magnesium in the product and the number of moles of oxygen. Again, it's simply the mole ratio. You weigh your empty crucible, put the magnesium metal in it, weigh that, subtract them, and we get the mass of magnesium. We all know how to convert mass into moles. It's simply mass divided by molar mass. Let's say we do that and we get the value of X, whatever that is. After you're done heating this and a few other little things, you're going to have the crucible with the product in it. Very carefully weigh that. The weight should have increased. It increases because we've added oxygen. So, crucible plus product added minus crucible plus magnesium gives a mass of oxygen. Same thing, mass over molar mass, moles of oxygen. Empirical formula, simply mole ratio, so it'll be MgO, Mgx, and O to the Y. Any questions? Again, really, really hot. Make sure you have goggles and be very, very careful. All right, Chapter 7, Aqueous Solutions. In this chapter, we're going to talk about dipoles and polar covalent bonds. Dissolution of ionic compounds, the concept of solubility and the nomenclature, electrolytes, non-electrolytes, solutions and the concept of molarity, and finally, dilutions. Starting here with polar covalent bonds. You recall we talked about bonding many times. It's something like chlorine. We have two nonmetals. They form a covalent bond between them. It's something like sodium chloride. We totally transfer the electron from the sodium to the chlorine and get a pair of ions. In reality, these two represent the limits of bonding. Most bonding is somewhere in between these two limits. When we make the covalent bond in chlorine, we start off with 7 valence electrons. We bring in another chlorine to give it Cl2. Each now has 8 because we count the shared twice. We tend to show these using the dash formulation, where the dash we recognize is a covalent bond shared, 2 electrons shared between the two. Now, when you have a compound that is covalently bonded, and you have the same atoms on both sides, you are probably going to get pretty good sharing between them. However, if you have something with different atoms in a covalent bond, this is hydrogen fluoride. The situation is much different. We're going to explore this using what's known as an electrostatic potential map. Electrostatic potential map is calculated by a computer. What you do is you start off with your molecule, and the computer calculates where in this entire molecule the electrons are. So you set it up, push the button, and it starts calculating. You wind up with a shell, and within this limit, there's a 90% probability the electrons will be there. All right. Next, you want to know the electron distribution, the charge. To do that, what you do is run a point over the surface, and as it goes around the surface on your computer's head, it calculates the electron density. You represent that in a distribution map by color. So we're going to take this and color it now. For hydrogen, this is beautifully uniform. Again, these are the same atoms on both sides. This is perfect sharing. All right, let's do the same exercise with hydrogen fluoride. For hydrogen fluoride, first we're going to calculate where the electrons are. We get a slightly different shape than we had with hydrogen. With hydrogen, it was beautifully symmetrical. But the real surprise comes when you do the electron distribution. Remember, we're going to color this to show distribution. And for HF, it winds up looking like this. Now the convention is you use blue to represent electron deficiency, which means that this end is positive, and you use red to show excess electrons. So this is negative. What has happened here is that the fluorine, this guy, has basically grabbed all of the electrons in this bond and moved it towards itself. We compare the two, the shapes are totally different, and of course the coloration is clearly different. This is a very nice little Easter egg, isn't it? When we have a polar covalent bond like this, we call that a dipole. And we can show it with a dipole moment like this. Basically, it's an arrow you put a cross on one end. This end represents the positive portion, this end the negative. Now, why does this happen? This happens because of the concept of electronegativity. Electronegativity simply is the ability of an atom to attract electrons towards itself. In the periodic table, there's kind of a ramp. It increases as you go across, it decreases as you go down. These are the least electronegative, and these are the most. With HF, we're dealing with hydrogen and fluorine. Fluorine is essentially 4, hydrogen is 2.2. That means that hydrogen or fluorine has a much greater propensity to attract the electrons towards itself. That gives us our polar covalent bond. Okay, so that's what a polar covalent bond is. The electrons are attracted towards the most electronegative atom in the bond. Simple concept. But in this chapter, we're talking about water, aren't we? Well, water is a bond between hydrogen and oxygen. Oxygen is almost as electronegative as fluorine. The prediction here is that the hydrogen-oxygen bond will also be highly polarized. So let's explore that. Let's start off with the Lewis structure for water. Oxygen is here in group 6, so it will have 6 valence electrons. Hydrogen, of course, is group 1. It has 1 electron for each hydrogen. We convert these to dashes, and that's water. Now, you might sit there and say to yourself, okay, that makes sense, but why are these drawn at right angles? Well, they're drawn at right angles because really this is a better representation of what water really looks like. Water really looks something like this. Oxygen in the middle, we have our 2 hydrogens, and we have 2 unshared pairs of electrons. There's a theory called electron shell or valence shell electron pair repulsion theory, VSPR. And what this tells us is that if you want to know the geometry of a molecule, you look at the central atom and ask how many things are attached, where things are either covalent bonds or unshared pairs of electrons. With water, we have 4 things. The theory tells us that means that water must be bent. It's bent because this is what's called tetrahedral geometry. Let's just do very quickly Vesper. If we have a central atom here with 2 things attached, two covalent bonds or whatever, the way that these can get the furthest apart from each other, this is electron repulsion, is if this has linear geometry. This and this are as far apart as they can get. So that's 180 degrees. If we bring in a third, we wind up with 120 degrees each in planar. This is tetrahedral. We have 4 things. Again, this is the geometry that puts all 4 of these as far apart as possible. This is the geometry of water, simply tetrahedral. Any questions? Yeah.
That's the fourth thing that I introduced on top.
Say that again.
The fourth thing, like you said, there was
Four
only
things, four things are either unshared pairs of electrons or covalent bonds.
Okay, so that's the unshared.
Yeah. All right. We looked at the table of electronegativities, and we said that oxygen was going to be 3.4, hydrogen is still 2.2. Our prediction here is that this OH bond should be polar. Now remember, we can show a polar covalent bond with a simple dipole moment. Again, the prediction is this is going to be positive. The electrons are sucked towards the oxygen. We can confirm that, or these two will combine. The global prediction for the whole molecule is that this end down here by the hydrogens is going to be positive, and this end by the oxygen will be negative. So what we get is a molecular dipole. The molecular dipole looks like that. This end of the molecule by the hydrogens will be positive, and this will be negative. We can confirm that by looking at the electrostatic potential map for water. And when we do that, again, we see the big blue bottom down here, that's positive. The negative oxygen up here, and there's our dipole. All right. The conclusion here is that water is polar. Water by itself as a molecule is highly polar, has a positive end and a negative end. Now, a long time ago, we talked about mixtures. We said that homogeneous mixtures were also known as solutions. It is the polar nature of water that allows it to form homogeneous solutions with ionic compounds. This is why water can dissolve salt, for example. And this is a little movie showing it. This represents a salt crystal, sodium chloride. The big green balls represent chloride. Sodium is a little gray thing. When I click the button, water molecules will diverge upon this. They will pick the ions off of the surface of the crystal one by one and carry them off in solution. So it looks something like this. Come in, grab a sodium, grab a chloride, another chloride goes, another sodium, etc. And they're carried off into solution to make the homogeneous mixture. Well, I hope you were paying close attention to this little video, because the way water interacts with these ions is different. Whenever the water interacted with a sodium cation, something positive, the sodium was surrounded by waters, but with the oxygens pointing in. When the chloride interacted, it was surrounded by waters with the hydrogens pointing in. The reason for that, this is the positive end of the molecule, and this is a negative ion. Over here, this is the negative end of the molecule, and a positive ion. What the water is doing is it's taking this charge and it's dispersing it over a larger area. Nature really doesn't like charged things. That's why salt clumps together. This allows the charge on the ions to be dispersed, makes it more stable, hence we get solution. Again, we can explore that with an electrostatic potential map. What you do is you tell your computer to take a sodium cation. Now it's positive, so it's bright blue. And we're going to put 3 waters around it with the negative ends pointing in. You ask the computer to first of all figure out where the electrons are in this complex, then where the charges are. When you do this, you start with our big blue ball, lots of positive charge, and we wind up with kind of like a green triangle sort of thingy. In fact, where we had the big blue ball here in the middle, we actually now have a yellow spot. Again, the water has taken the charge from the sodium cation and dispersed it over this complex. Now in the next chapter, chapter 8, we'll expand upon this because water doesn't just exist in clumps of 3, it actually does 8 or 12 much better. And this effect in water is phenomenal. Water is able to stabilize ions better than any substance that we know of. That's why water is so important to life as we know it. All right, so we can take these ions, surround them with water, disperse the charge, and they go into solution. Let's talk a little bit about solutions in general and the concept of solubility. If something dissolves in a liquid, it's said to be soluble. Solubility actually refers to an amount. The solubility of magnesium carbonate is 0.53 grams per liter of water. So it's a number. The term solubility is a number. When you take magnesium carbonate and you manage to dissolve 0.53 grams in 1 liter, that's the maximum amount. And we say that that solution is saturated. Solvent, the term means the thing doing the dissolving. Solute is what is dissolved. Simple nomenclature. Again, solubility actually represents a number. Any questions? Well, the concept of a saturated solution is interesting. You can actually cheat and make what's called a supersaturated solution because the solubility actually depends upon the temperature. This is 298 K. We don't know what K means, but this is room temperature. Chapter 9. If you heat up the water, more will dissolve. And for many compounds, you can actually get more in than you're supposed to. That's referred to as a supersaturated solution. So think of fries. That's a fry. And you could super fry it, right? Supersize it, whatever. Way too much. One compound that does this very, very nicely is sodium acetate. Again, you'll meet sodium acetate in general chemistry a lot. It is very soluble in water, and you can heat it up and just keep putting more and more and more in, and it will dissolve nicely. And if you're extremely careful with it, let it cool down very, very slowly. You can wind up with a supersaturated solution like this one, where we have 2 or 3 times more in there that should be there. Okay? The neat thing about a supersaturated solution is you can make it come back to saturated. What we're going to do here is take this flask, put it up there, and we're going to drop a single crystal of sodium acetate into the liquid. What we do, it will set off a crystallization reaction that is so neat to do. Let's watch. It's going to land about right there. The second it does, it sets off crystallization. Everything reverts back to a saturated solution. In fact, this thing will just totally set solid. The liquid that's still in there will be saturated, and this is all the liquid or the solid that we managed to get in at a higher temperature. This also gets really hot when this does. That's because we put the heat in. The heat is still there, the energy is still there, and when it crystallizes out, the heat is given off, and this is, like I said, it's really hot. Any questions? Kind of neat. There's a rule for solubility, rule of thumb, and it's simply like dissolves like. What we're comparing here is polarity. If we have something with a polar solvent and we have polar covalent bonds, they are very likely to dissolve in each other. This is water, and we're adding alcohol to it. The two are miscible in all proportions, and that's because alcohol, this is ethanol, has an OH group just like water. Only has one OH, so it's not as good at doing things as water is. Still, the two are totally compatible with each other. Compare that to this. This is oil being drizzled into water. Water is very polar. Oil is basically CH bonds that are not polar. So a nonpolar solute, polar solvent, they don't mix. Simple rule, like dissolves like. Any questions? All right, electrolytes and non-electrolytes. You may be aware that you're not supposed to go in a bathtub with a hairdryer, right? It's a bad idea because you'll get shocked, right? Well, the reason that you can get shocked by a hairdryer in the bathtub is that the water will contain ions. Tap water contains dissolved ionic compounds. When you have ions in water, that will conduct electric current. If you had absolutely pure water with no ions in it whatsoever, it wouldn't conduct electricity. It would be what's called a non-electrolyte. One of the standard lab experiments that they do in general chemistry, that we used to do in 110, is to measure conductivity for electrolyte and non-electrolyte solutions. This goes way back. When I was a child taking chemistry, we also did it. This is the apparatus that we used very, very long time ago. It had metal plates that you dangled into a beaker of solution, a light bulb. And where do you get the electricity? Well, you plug it into the wall. Now think about that. You've got a full class of these chemistry students that don't have a clue what they're doing. You have solutions that can conduct electricity, and you're putting 110 volts into it. It's a bad idea. Really, it's a bad idea. Very dangerous experiment. This was a non-electrolyte, so there's no ions. Your light bulb does not light up. If we put a different solution here, one that has ions in it, plus and minus, these will move between the plates. They will carry the electricity as they go, and you get a nice bright light. There's something in between our two limits here, and that's called a weak electrolyte. So you have something that has some ions, but not all. In a weak electrolyte, something like acetic acid dissolves in water nicely because it's very polar, and it will ionize to form hydronium and acetate anion. But the ratio of these two is roughly 100,000 to 1. So there's only a tiny bit of ions formed from acetic acid. Because of that, instead of the bright bulb, we get one that is dimly lit. Now this is the way it was when I was young. Today, we have instruments that are much, much safer to use. It's a conductivity meter. This is a solution that's an electrolyte, and you can get a digital readout in microsiemens per centimeter of the conductivity. So we get a big number for an electrolyte, lots of ions. Weak electrolyte, we get an intermediate number. And if we just had pure water here, we don't get 0, but we get a small number. The reason we don't get a 0 here will become clear when we do chapter 8. Any questions? As a simple summary of electrolytes and non, if you form ions, it's an electrolyte. If you form a few ions, it's weak. And if you have something that dissolves, again like glucose, but does not ionize, does not form ions, it's a non-electrolyte. And here's our little sodium chlorides, again surrounded by water. Positives towards the negative, negatives towards the positive. Any questions? All right, well, we can't let a whole chapter go by without doing some calculations, can we? That would be such a shame. So, we will now introduce the concept of molarity. Lots of reactions happen in solution. In the last lab, you did a bunch. Did precipitation reactions, did solution, right? In order to know, or in order to be able to do these quantitatively, you have to know how many moles you're dealing with. Molarity does that for you. Molarity is simply defined as the number of moles of solute per liter of solution. This must be liters, and this must be moles. Number of moles divided by volume in liters. The way that we do this in lab, we use what's called a volumetric flask. Volumetric flask is an expensive piece of glassware because this is a 1 liter volumetric. It has a little line etched in it. That etching is done by hand. They put exactly 1 liter of water in the vessel at exactly 25 degrees, and the volume comes up in the skinny neck here, right at the little edge line. So, if you have a solution here, you now know the volume exactly, right? So we know the volume, we know how many moles we put in there, and molarity is simply 1 mole per liter. That's silly, but the way you actually do this in lab does make a difference. What you do, we're going to again use our volumetric flask here. The reason it makes a difference is that there are 2 ways to measure concentration of solutions. One is molarity, which is an uppercase M, and the other one is molality, which is a lowercase m. Have to be careful how you write these things, right? In general chemistry, molality, it's a cruel joke that they play on you, nonetheless. To make a solution of known molarity, what we'll do is start off with our empty flask. We will then weigh out a solute, a certain amount, a certain numbers of things, and we will add it to our flask while it's empty. So here we go. Now, we know the number of moles that we put in there. We will now add water very carefully, right up to the etch mark for 1 liter. We now know our volume in liters, 1, and we know the number of moles because we weighed them and put them in there. With molality, you do it differently. You put in your liter of water first, then you add the solid. So, slightly different, but we use them for slightly different things. This is molarity. Let's go ahead and do a simple problem. We have 3.25 grams of sodium bromide. That's its molar mass. We have a solution that is 1,250 milliliters. What is our molarity? Well, we remember, molarity is simply going to be the number of moles divided by the number of liters. To get the number of moles, we are given a mass, and by George, we know a molar mass, don't we? What is mass over molar mass? It's moles. So we take our mass, divide by our molar mass. This will give us the number of moles of sodium bromide. Next, we need to divide that by the volume in liters. There are 1,000 milliliters in a liter, so we divide this by 1,000, and that's our volume in liters. Now, obviously, grams are going to cancel, and in our denominator of the numerator, we have moles to the -1. Think about it this way. This is a reciprocal, isn't it? Anything to the -1 is a reciprocal. So we have 1 over, 1 over. If you do that twice, if you take something, flip it over twice, you're back where you started. So, per mole comes up as mole. Our units will now be moles per liter. The math is very simple. 3.25 divided by 102 divided by 1.25. 0.253 moles over liters. Moles over liters. That's the definition of mole. Uppercase M. Quite often, so that people know that this means molarity or moles per liter, people will use an italic M or an M with a line underneath it, or even a script M. The only thing you have to make sure is that it is uppercase. Whenever you see an uppercase M in chemistry, think moles per liter. Any questions? That's simple to do, isn't it? Well, let's do it again then. This is sodium acetate. We met that guy. We have 6.7 grams of it, 1450 mils of solution. Calculate the molarity. Again, convert our 6.47 to moles, convert our milliliters to liters, and do it. Why don't you set it up? To get moles, we simply need to take mass divided by molar mass. Mass divided by molar mass gives us moles. Divide our 1450 milliliters by 1,000, 1.45 liters. The math. These cancel, that goes up. 6.47 divided by 82 divided by 1.45, 0.0544 moles per liter. Sometimes you'll see this written out as moles in liter minus 1 because it's in the denominator. Probably best to use uppercase M to show that this represents molarity. Any questions? All right. Here's one more. Potassium hydrogen phosphate, 238 grams, 275 milliliters. Again, set up the equations for me. We have a mass, we have a molar mass, that gives us moles. Divide our 275 by 1,000, that will give us our volume. Grams cancel, per mole comes up. Do the simple calculation, 238 divided by 174 divided by 0.275, 4.969. We have three significant figures, so we round it to 497. Sound reasonable? All right, there are tutorials for this. The first one is a table tutorial. I believe it's called Mole 1. Molarity 1 or something. And everybody loves tables, right? We need the molarity. We are given moles. We are given volume in liters. We recall, molarity is simply moles divided by the volume in liters. Substitute in 0.976 divided by 2.15, 0.454. I can pretty much guarantee that on exam number 2, you will have a table like this, at least one, with one thing blank. Here we have the volume blank. We know the molarity, we know the moles. Right? On your little 3x5 card, just so you don't forget, you have written down molarity as moles divided by liters. All right, we are solving here for liters. Liters is going to be moles divided by molarity. We have moles per liter. Simply do the division for 0.26 liters. And let's do one more with moles missing. Again, to get moles, we're going to take molarity and multiply it by our volume. Moles, molarity multiplied by volume. Here's our molarity, here's our volume. We're 0.35 or 0.365 moles. Now what we have just done here is something else that is worth remembering. We have taken a concentration of a solution. We've multiplied it by its volume. And what do we get? Moles. Concentration times volume is moles. That is also worth writing down because it's a very useful expression. We'll use it a lot. All right, let's pretend that we're in lab. Good times, right? We have a solution that's 0.18 molar KCl. The lab that you're doing requires that you have 0.01 moles of KCl. How much stuff do you need? A real-life lab experiment. It's a stock solution, right? You're going to pull some out, a certain volume, to give you 0.01 moles. Molarity is moles divided by volume. We need to divide moles by moles per liter to get our volume. So we take this, solve it for volume. That's what we're looking for. Liters of solution. Here's our number of moles. Moles of KCl. Here's our concentration, moles per liter. Moles cancel. Per liter comes up. 0.056 liters or 56 mils. So in lab, you would take your stock solution and you would measure out 56 mils and know confidently that that's 0.01 moles. It's a real life problem. Any questions? Since we're dealing with moles, we can also do all sorts of other things. How many sucrose molecules in 300 mils of a 2-molar solution? Well, how do we get molecules? Avogadro told us 6.02 times 10 to the 23rd things per mole, right? So, we need to figure out the number of moles. How do we do that? Concentration times volume. Once we know the number of moles, we use Avogadro's number to get molecules. So, molarity is moles divided by volume. Concentration times volume is moles. Remember those. Concentration times volume. That's going to give us moles. Liters cancel. 0.375 moles of sucrose. Once we know how many moles we have, we can use 10 to the 23rd molecules per mole. Moles will cancel, and we are left with molecules. 2 times 10 to the 23rd molecules. Any questions? So you can just use these things interchangeably and make all sorts of problems. When you take potassium sulfate and you dissolve it, what happens? Well, when we took sodium chloride and dissolved it, the sodiums went here, the chlorides went here, they're all mixed together. Here we have two potassiums, right? The question is, how many moles of potassium are there? How many moles of sulfate are there? We have a concentration and a volume, so that gives us moles, doesn't it? To calculate moles, we need to know how many moles of potassium sulfate there are, multiplied by the mole ratio to get moles of sulfate and moles of potassium. So what's really happening here? We're going to take our potassium sulfate, going to put it in our beaker of water. The second we do, it will dissolve. And what are we left with? We're left with sulfate, 1 sulfate per mole, and 2 potassiums per mole. That's our mole ratio, right, of ions. These things will totally dissociate. So, moles of potassium sulfate, concentration times volume. Multiply those together. Liters cancel. 0.38 moles of potassium sulfate. So to answer the first part, how many moles of sulfate? Our mole ratio, 1 sulfate per every potassium sulfate, multiplied by the number of moles. Moles of potassium sulfate cancel. This is 1. 0.38 moles of sulfate. We have 2 moles of potassium in our every potassium sulfate. So the ratio here is 2 to 1. Multiply 0.38 by 2. 0.76 moles of potassium. What this is designed to make you realize, make sure you understand, when you dissolve an ionic substance like this, everything dissociates into ions. So we have 2 potassiums for every sulfate in solution. Our second tutorial, mole mass relationship. Wet volume in mils. So this, you have to do a couple conversions here probably. Wet volume in mils. Here's our concentration of methanol. Here's its molar mass. We want 0.03 moles of solute. All right, we have a concentration. We're looking for a volume. Moles is moles divided by liters, that's molarity. Liters is going to be moles divided by molarity. Substitute in 0.666 liters. Remember the problem asked for this in milliliters. Do this, 666 milliliters. This looks the same thing, the same way on Blackboard. Any questions on this one? Do another. Here we're looking for milligrams. We have a volume, we have a concentration, we have a molar mass. Again, we're looking for mass. We remember that mass, or the number of moles, is molarity, concentration times volume. Substitute in, we have 0.87 moles. Convert this using a molar mass, and moles times molar mass is grams, multiply them out, we have roughly 28 grams of stuff. The problem asks for milligrams, 1,000 milligrams per gram, multiply it out, 27,900. Okay, well, just like with the first tutorial, we did mass here, we did volume. There's a volume in pills, 0.175 calcium nitrate. What volume? And we want so many moles. Go ahead and set this up. We're looking for volume here. That's going to be moles divided by molarity. And moles divided by molarity. And we want this in mils. Moles divided by molarity is our volume in liters. Substitute in, convert to milliliters, 50 mils. Any questions? Well, an obvious question is, what's going to be on the exam, right? Let's do a couple exam questions. Molarity of a solution that has 10 grams of sodium hydroxide and 500 mils is what? Well, all we have to do to calculate molarity is know moles divided by liters, right? Molarity is going to be moles of sodium hydroxide. 500 mils is 0.5 liters. How do we get moles of sodium hydroxide? 10 grams divided by 40 grams per mole. 10 divided by 40 divided by 0.5 gives what? It's about 0.5 molar. It's a nice simple question for the exam. How many grams of calcium nitrate do we have to dissolve to make 500 mils of 1 molar solution? A 1 molar solution has 1 mole per liter, right? We're dealing with half a liter. We have half a liter, or we want a solution of 1 mole per liter. The number of moles, this is a concentration, here's our volume. We're dealing with half a mole. All right. How many grams in half a mole? Here's our number of moles, here's our molar mass. We simply multiply these together. 0.5 times 164. Oops. There was an answer to that. 82 grams. Let's do another. We have a solution that is 0.375 moles per liter. Total volume is 0.475 liters. How many moles do we have? On the exam, this was actually an extra credit, so you had to show your work. We know concentration, we know volume. That means we know moles. What you did on the exam was to take concentration multiplied by volume to get moles. And it looks like this. 0.375 moles per liter, 4.75 liters, 1.78 moles. One or two more. Here we have a sodium chloride solution, 200 mils of it. We're going to let it just sit and evaporate. All the water's gone. We recover 1.5 grams of sodium chloride. What was the molarity of the original solution? Same problem over and over again, isn't it? Our molarity here is going to be moles of sodium chloride divided by our 0.2 liters, 200 mils. Moles of sodium chloride, we recovered 1.5. 58 is our molar mass. Simply take 156 divided by 58 divided by 0.2. We're looking at 1.33 moles per liter. Any questions? Lots of varieties, but it's the same simple problem. Molarity is defined as moles divided by liters. Just manipulate those three things that you can solve for anything. All right, our last topic in this chapter is dilution of solutions. There are two types of dilutions that we'll talk about. One we'll just talk about, and the other we'll do problems. The first one is called a serial dilution, and it's kind of a neat thing because it allows you to make extremely dilute solutions. For example, we have a stock solution with something in it. We know the molarity. We take 10 mils of it out, add it to 990 mils of water. We wind up with a liter that has been diluted 100-fold. Take 10 mils of this, add it to more water. It has been diluted another 100-fold. 10 mils again, another 100-fold. So this is 10 squared, 10 to the 4th, 10 to the 6th. So the concentration here is 1/1,000,000th of what it was here. You can't weigh that out. So doing a serial dilution, you can have a known concentration that's very, very, very dilute. Now, this is useful in the lab. If you need a solution that you can't weigh out a milligram, say. But you could take a solution and dilute it 1,000,000-fold, and that's no problem. This is the same procedure that's used when they make homeopathic medicines. Homeopathic drugs are not regulated by FDA because they do so many dilutions, serial dilutions. They wind up with a solution that has basically nothing in it. Okay? You do the same thing here. You start with a milligram of stuff in solution here. Here we have 10 to the minus 6 milligrams, a billionth of a gram. So, homeopathic drugs. Now, when I was a child, ever heard of strychnine? It's an organic compound. It's a poison. It comes from the strychnine tree. You used to be able to go into a drugstore, go into Walgreens, and just buy one of these. It was very useful. You could use it to kill rats. If you were upset with your spouse, you could poison them. It was, really useful stuff, okay? Well, you can't do this anymore. You can't go into Roscoe and buy strychnine. But actually you can. It comes in a tablet form, and it's for cough relief, and it's called Cold Calm. Children's Cold Calm. Yes, the active ingredient in children's Cold Calm is strychnine. Well, but it's homeopathic. That means, here's our active ingredients. And these three are the real winners. Belladonna alkaloids. 0.2 milligrams will kill you. Okay? But in a tablet, there's 10 to the minus 14 milligrams. This guy, yellow jasmine is what it actually is. It's related to strychnine. It's a little bush. If you're walking through the woods and you walk through a patch of yellow jasmine and you're wearing shorts, you will get enough absorbed through your legs to kill you. This is diluted 10 to the minus 12 times. And the lovely Nux vomica here, that's strychnine. It is the highest concentration, 10 to the minus 8 milligrams. Again, none of these are going to do anything for you, good or bad. You're not going to poison your child, no matter how upset you are with them. But it's fun to think about sometimes. I have 4 sons. All right. The other type of dilution, we take a solution where we know its concentration and we add water. When we do that, we wind up with a new solution with a different concentration, right? The thing that's important to note here, though, is we start off with a solution. We know how many moles are in there, right? We change our volume, but the number of moles does not change. The number of moles does not change. We know how many moles we have because we know concentration and volume. If V1 is our initial volume, C1 is our initial concentration, multiply these together, we get initial moles. Final, V2, C2, final number of moles. But these two are the same because they don't change. Therefore, V1, C1 must equal V2, C2. So to do dilution problems, this is what you write on your little 3x5 card. V1, C1, V2, C2. Let's see how it works. We have sodium chloride, 0.53 moles per liter. We have 500 mils of this solution. We add water till we get 1750 mils. What's our final concentration? So we're looking at concentration times volume initially, concentration times volume in the final state. We're looking for the final concentration, that's C2. Simply take this, rearrange it. C2 will be V1, C1 divided by V2. Do our division. We will cancel liters and be left with concentration. 0.15 molar. The key thing here is this simple equation, because the number of moles does not change. Do another one. What volume of 2.1 molar is needed to make 1,600 mils of 1.1 molar? We're solving here for the initial volume. What volume of this molarity to make this volume of that molarity? V1C1, V2C2, and again, we're solving for V1. C2, V2, C1. Molar will cancel. 1.1 times 1.6 divided by 2.1. 0.84 liters, remember the liters, or 840 mils. Now you can make these problems as difficult as you want, but I have. This is as difficult as I want to get, okay? They're straightforward, C1, V1, C2, V2. There's a tutorial for it. What final volume are we looking for? That's V2, right? We have 140 mils of 2.3, that's V1, C1. Final concentration at C2 of 0.56. There's our basic equation. Again, we're looking for the final volume as V2. V2, C1, V1 over C2. Substitute in 0.58 liters. The problem asks for milliliters, multiplied by 1,000, 580. Let's do one more. mils, 0.51 moles, that's V1C1, is diluted to a final volume of 0.88. That's our V2. What is the final concentration? So again, we're simply solving for C2. C2, C1, V1 over V2. Substitute in. Do the simple math. 0.026 molar. The tutorial on Blackboard is just as simple as this one. Please remember, you only get credit for Blackboard stuff. This is fun to do. Blackboard stuff gives you points. Now, that's the end of this chapter. There are a couple things I want to say. On Monday, we are going to do Chapter 8. Chapter 8, acids and bases. Please bring your calculator. Okay? Make sure you know how to access the buttons for log and the buttons for 10 to the x. Also, remember on Wednesday, we're doing our flaming lab. Please bring your goggles. Be very, very careful with this guy. It is literally red hot. And finally, here's our list of tutorials. We added 3 today: molarity 1, 2, and dilutions. 5 points each, you're shooting for 350. Do it. All right, have a good day. See you on Wednesday.